All right, how about now? Can anyone hear me?
Yes.
Thank you. All righty. All right. Nope, that's worse. All right. Well, everyone, let's dive right into our next section of material. So we're moving on to our next chapter, and this is going to be on electromagnetic induction. All right. This is a big one. Honestly, this is my favorite chapter, guys. I absolutely love all this material. So we're just gonna dive right into this. We're gonna start building up to what the heck do we mean by induction? Before we can do that, we have to talk about a different concept called flux. We vaguely talked about flux before, but as a reminder, right? We're going to define magnetic flux. Right? Magnetic flux, we'll give it a symbol of a capital Phi V, right? Right? So this magnetic flux is the amount of magnetic fields passing through an area. So the amount of B fields passing through a oriented area, right? Very mathematical. Let's try and have a picture of this. Let's say I have a blob, right? I've got some blob in space, right? And I can associate a normal vector. I can say, look, there is the orientation. So I've got my blob and it's oriented some direction. If it helps, right? Take a piece of paper, right? And it actually has some orientation, right? The paper's facing you. Now it's facing to the right. Now it's facing up, right? That's all I mean. And I'm gonna say, all right, there's some magnetic field lines penetrating this surface. So magnetic flux says, okay, how much are these field lines going through this thing? Right? If you want a analogy, this is one I like to use a lot. Think of a water hose, right? You've got your pipe, and you've got all the water behind it, and it flows out of the pipe. Right? Now, if you're playing with your hoses, all right, your kids or just having fun right now, you're playing with your hose and you want to spray your friends, what do? You introduce your thumb and you block part of the hose. And so you have all this water trying to push out of the pipe, and yet you're blocking some of the area, right? That's gonna be key. You're blocking some of it. So what happens to the water? It flows out faster and then starts to spray, right? So, key ideas. Flux depends on amount of stuff, and the area stuff is passing through. So going back to my magnetic flux, this blob, whatever it is, has some amount of area associated with it. And so when I ask what's the magnetic flux, I'm saying, well, how much do these field lines pass through that area? Right? Think of the water analogy. Magnetic flux, think of how much is flowing through. No questions yet. Right? So instead of a blob, let's go for a nice rectangular shape. Right? So here's my rectangle. Let's give that orientation. Right. So once again, this is equivalent to, here's my piece of paper, and here's the orientation. That's what I've drawn. Right? Paper, orientation. Right. This, I'm going to call it the area vector. Right? It's just the length of this is how much area is in the square. And we'll start pushing magnetic fields through it. All right, notice area and magnetic fields, they are parallel, right? Think kind of like this. The water's flowing out of the pipe. The end of the pipe and the water are going the same direction. So you get maximum flux. That's my area. And here's my B field. Then I can say, what's the angle between them? Right? 0 degrees. Well, now let's twist this. Instead of having the paper like this, I'm going to flip it up a little bit. So now I'll have it's now off at some angle, and here comes the magnetic field lines. They pass through, right? I've changed the orientation, but not the direction of magnetic fields. If I just focus on one, here's A, there's B as it passes through. There is some angle between them, some angle phi. Right? And I've decreased the amount of flux. One more case. So I've gone from paper oriented this way to at some angle to pointing straight up. So now I'll have my paper this way. Now no magnetic field goes through it. All the magnetic field does is go across. Well, but focusing on just one again. Right? They are 90 degrees, they're perpendicular. No flux. Right? So you go from phi equals 0 degrees by, let's call this one 30 degrees. Right. At 0 degrees, I have maximum flux. 90 degrees, no flux. So we're saying, hey, as I change this orientation, I change the flux. And if you haven't guessed right now or looked ahead, This is going to look like a trig function. Has to. So what we'll find out is that the flux, magnetic flux, goes as the magnetic field strength, area that's being passed through, and a cosine. Cosine the angle between them. Phi b, little phi. The flux goes from maximum when the angle is 0 to a minimum at 90 degrees. All right. Still no questions, so we'll keep moving along. All right. So we still haven't gotten to induction. All we've done is talked about this weird flux thing that we're going to be computing a lot of these soon. But some comments. I have this magnetic flux. Remember, think area and how much something flows through it. Right? This is what I mean by flux. That's the picture that should be in your head. Now, what can I do to change the flux? Right? I say there are 3 ways to change flux. And this is going to be absolutely crucial for us when we start talking about induction. Right? So, method number 1, right? Change field strength. Change how strong the magnetic fields are going through that thing. Right? I could have my square loop with not a lot of fields going through it. Or I could have, let's put a barrier between here. Or I could have a ton. Right? I increase the number of magnetic field lines. I've increased the flux. Going back to the water pipe analogy, you've increased the pressure of the water going down your pipe. Right? So that's the first way to change the flux. My second way is to change the area. Right. So what do I mean? Here is similar pictures before. Here's my little area. And imagine I take my piece of paper and I stretch it out. I make it bigger, while keeping the same magnetic field strength. So I've taken the area, in one picture I made it bigger, or I could shrink it down. I changed the area, boom, I've changed the flux, the array. Right? So one method said change B, second method, change A. All I'm left with is the angle, so I changed the orientation. Change the orientation. I could have, right, my good old favorite square loop, some magnetic fields going through it, And then I could say, rotate it. I just rotate it. And now I say, oop. Right. So, any questions so far about this new concept, magnetic flux, and my 3 ways to change it? All right. I see no questions. So let's go to a little simulation. If the world wasn't blowing up, I'd actually have a demo of this, but I've got computer simulations to back up. So let us share that. All right. So we're trying to tie in this concept of the flux to our electricity and magnetism. So here's the setup. Let me pull up. Oh, go away. Where am I? All right, here we go. So can everyone see the little computer simulation I've got up on the screen now?
Yes.
Thank you. All right.
It looks pretty cool.
Thank you. Thank you. These are all from Colorado University. These are called PhET simulations. I will be sharing links to these. I strongly encourage everyone to try and play around with these things. So here's the setup. I've got this little coil here, right? And that's going to be our area. One loop of this coil will be the area we're passing through. And I have myself a little bar magnet. And I'll say, all right, let's put this guy here. And there are magnetic fields passing through this. So you can say that there is a magnetic flux. There is some flux through the solenoid. And now I move the magnet and nothing's happening on the light bulb. It just stays there. But watch carefully as I slide the magnet around. Look at the light bulb.
Okay, I don't see anything happening.
No one sees the magnet moving around?
No, I don't see anything moving either.
Okay. Let's see here. Let's see here. Let's stop the share. All right. Magnets moving?
Yes, I can see it.
Yes.
Awesome. Okay.
I can see
So
it.
let's do that again. So, all right. So I can turn on magnetic field, and you can see as I move the magnet, the compasses will reorient themselves to point at the magnet. All right. So I'm going to turn off the field, and there's my solenoid. I'm going to bring the magnet close to the solenoid and watch the light bulb. Right. So keep the magnet there. There is flux. There's flux happening, and the light bulb doesn't turn on. But in think of
Oh,
what,
Wait,
what was that? Here.
I think he might have forgot his mic was on.
Gotcha. All right. So put the magnet in the solenoid. There is flux. There's definitely magnetic field lines going through the solenoid, but nothing's happening. But then I say, change it. If I change it, if I'm moving the magnet around, you see the light bulb turns on. I'll turn the field off. So now we can play around with this, okay? I'll have the magnet move slowly. And you see dim lights coming on. Now, if I move quickly, if I move fast, the faster I move, the brighter the bulb. The slower I move, the dimmer. Yes, exactly. The quicker I move, the brighter the light gets. Right. So the emphasis here, I have magnetic flux. Here, let me switch to, let's see here. All right. So I switched to the simulation. It's got like the blue background now. Right. Basically the same thing, but the field lines are prettier. Right. So I've got the white field lines going through the solenoid, and I can move the strength of the field through the solenoids. Faster I move, the greater the induced current, the brighter the bulb.
So is it like it's charging it?
It's charge is starting to move in response. That's the key thing. It is being charged because these magnetic fields are moving through there. And this is the key concept. Look, when the magnet's just sitting there, no current flows. But as soon as it moves, current flows. Charge is moving in response. And that's our induction. That's our magnetic induction. If I change the flux, there is a current that starts to flow in response. All right. Let's come back to the board. All right, so critical idea. There must be a connection between, let's see where are my notes, between magnetic flux right? Move the solenoid around, a current flows, the light bulb turns on. So there must be some connection. And we notice that not only was it was flux, it was changing flux, right? Ways I can change flux. I can change field strength, the area, the orientation. So all these changes happen in time. So let's do some unit analysis. All right. Unit-wise, what the heck is this? Change in magnetic flux, change in time, right? So unit-wise, this is magnetic. Let's see here. Let's see here. Units on flux equals a BA cosine phi. Magnetic, the units for magnetic field is a Tesla. Units on area, meters squared. Units on an angle, none. their angles are dimensionless. So, right. So a magnetic flux has the units of Tesla meters squared. I won't focus on this, but I should give it to you because what a lot of people do is they call this a Weber, which they call WB. I prefer Tesla meter squared, but a lot of resources like to define the Weber as the magnetic flux. Right. So back on the task on hand, what is the units of change in flux, change in time? So delta phi v, delta t. This is a Tesla meter squared over change in time. That's a second. All right. So I see something that looks completely foreign to me. So we got to break this down, simplify it to units further. So you remember what the base units of a Tesla is. Dead silence means obvious no. All right. Remember our units. You could use a previous equation that we studied. We studied forces and magnetic fields a lot. So recall, the magnetic force is QVB with a sign phi that we're going to ignore because we always make things nice and orthogonal. So we could say a Newton is a Coulomb velocity, meter per second, Tesla. So 1 Tesla divided by coulombs multiplied by seconds per meter. 1 Tesla is a Newton per Coulomb meter seconds. All right. Newtonian amp is a Newton amp. Close. You could express this as a, let's see, a Coulomb per second is amp. So it'd be a Newton per amp second. Or no, Newton per amp meter. So you can express this in terms of amperes. Right. So I'm going to take this version and plug it into this guy. So our change in flux, change in time is now Tesla's being replaced by this quantity. It is a Newton Coulomb meter per second times a meter squared per second. All right. Second per second. I've canceled the seconds. The seconds die. Meter squared per meter. I've got 1 meter left, so this is a Newton per Coulomb meter. Right. I'm slowing down a little bit, just to not overwhelm everyone. All right. Newton meter. Anyone remember what that's called? Still blank. So you don't remember what work is. Work is a force times a distance. So a Newton meter A Newton meter is a joule. So a Newton meter is a joule. I have a joule per coulomb. For the grand conclusion, delta phi b delta t. A joule per coulomb is a volt. Stand out of the way of the camera. All right. So emphasis. I said, let's make this text actually legible. Delta phi b delta t. Claim. I can define this weird concept called magnetic flux. It's how much the field lines penetrate a given area. If that flux changes, right? That's what the deltas are for. If that flux changes in time, a voltage is produced, an electromotive force. As I slide the magnet around the solenoid, I change the flux, there's an EMF, a voltage drives current. So by sliding the magnet, I can move charge. All right. So I cannot overemphasize how important this law is. We literally call it a law of our universe, named after the guy who first connected these concepts together. It's called Faraday's law. This is a fundamental law of the universe. You need to know this, and we're going to express it in a lot of different ways. So, in essence, an EMF, a voltage, an electromotive force, an EMF is equal to the change in magnetic flux over time. And for now, we're saying just the magnitude. We're not going to worry about signs yet. Right? We're going to say calculate change of flux, how much time has transpired. There's your voltage, your induce. Now that I think of this, wiggling my magnet around, I make a battery. I'm the battery now. I move the solenoid. I become a battery to move some current around. Right? So the emphasis. A change in flux induces an EMF. And that's why we call this induction. This whole chapter is off of this result. Change in the flux induces current. I think I see a question. Let's see here. Is this how we proved in our RC circuit lab? Sounds right to me. All right. So, as always with me, let's do some examples to put weird abstract math into some context. So, all right. Here's my example. I'm going to go with a square loop. A square loop of side length 5 centimeters is in a uniform magnetic field of strength 5 Tesla. Right? So here's the picture. Pretty much the same one I've been drawing all day so far. Right? So there's my loop. And now I'm going to do 2 cases with this. I'm going to do case 1 where I slide. along the magnetic field. Right? So case one, what's the induced E? Let's see here. If the loop is pulled to the right. All right, we're gonna be doing changes. I need to talk about how fast this thing is moving. And the number that I picked is 3 centimeters a second. I know there's a time component. So, case one, what's the induced EMF if the loop is pulled to the right at 3 centimeters a second for 0.1 seconds, right? So, I'm a very visual person, so we're gonna look at this from the edge to get an idea of what's going on. So I'm gonna have, here are my field lines, and they extend however far I need them. And here is my loop, right? So we're just looking at it on edge. That's what we're looking at in this picture to the right. We're just looking at on edge. So this loop has an area oriented that way. Right? We'll call this our initial case. This should remind you of, say, like energy conservation. I'm going to say, what's the initial state? What's the final state? We're going to be doing that again. Okay, so there's a question on, does the thickness of the object matter? Interesting point. And it turns out that thickness doesn't really matter. All right, so my example has always been just this weird flat loop, but like, let's give it some dimension, all right? Let's make it a true three-dimensional object. All right, so there's my three-dimensional object. All that matters is the area that's being fluxed through. Right? How thick it is doesn't really matter. All that matters is this area here, this 2D cross-sectional slice. Does the length. So length will matter, and that will play into this example shortly. So, so let's come back to this, and then I'll answer the length question because it will come up, right? So here's my initial state. I've got my loop. You can think of, right? Here's my loop, and I'm going to drag it to the right this way. So my final case. Right. And it used to be over there. All right, so analysis time. I said there are 3 ways to change magnetic flux. From initial to final, I have not changed the magnetic field. It's still the same fields. I'm still sliding on the same bars. I could change the area. Well, I haven't crushed this, I haven't stretched it. It's the same loop. So all I've done is change the potential orientation. Well, what's the angle between the field lines and the loop? In this picture, 0 degrees. In this picture, still 0 degrees. So, in case 1, there is no change. There wasn't a change in the flux. All I've done is just ride along this bar, right? As long as the fields are staying constant, as long as blue lines are constant, I can slide left and right to my heart's content and not induce any current. So, case 1, there's no induced EMF, nothing. Right? Right. So, let's try case 2, where yes, we will get it. So, case 2, right? Same things, all right? What is E if the loop moves up? It's going to move out of the field at still the same 3 meters a second for 0.1 seconds. Right? So, here's my initial case. Here's my little area. And now the question of, will the length matter? In this picture, yes, it is going to matter. So let's go to our final case. This guy is moving up that direction. So the loop itself will have exited the field. The amount of flux has now been reduced because there's no field lines on this top part. There's some field lines now or before. Is that a new question? Nope. All right. I'm going to redraw these as if I'm an observer over here looking straight down, right? So I'm going to redraw these, right? As if I'm this person looking at this thing doing this. So what I see is magnetic field lines coming towards me, and I see a square loop or a rectangular loop going out. So redraw this. Right? Magnetic field lines. They are coming towards my eyeball in my new picture. So I'm going to see a bunch of dots. And here's my initial loop. There's that 5 centimeters, 5 centimeters. I'm going to call that little a. Little a is 5 centimeters, right? Now let's separate those. Draw this picture again for the final case. The loop has moved up, out a little bit. So I'm going to have just that. So right. The area has now changed. I went from, right, I'm going to use pink to highlight the area that's being fluxed through. initially, the whole loop is getting flushed with magnetic field lines. And then in the final picture, only part of it is getting flux through it. So I'm going to call this height, this length, B, right? And I'll say area is function of time. So area as a function of time equals side length A times side length B. Right? So the A, right, the little a, that 5 centimeters, this does not change in time, but this guy, little b, that does change as I pull this out of the loop, right? So this B, before I pull the loop out, B is the full 5 centimeters. Let's make a little plot of this. Right. At t equals 0 seconds, I am at some 5 centimeters. B is the full length of the loop. As I pull the loop out, B decreases in time. B shrinks, so it must go down. All right. Right. So slope, right? What's the slope of a position versus time graph? The slope on position versus time is the velocity. So I can just say, look, v as a function of time is going to equal the initial, that intercept, which is a, 5 centimeters, minus velocity times time. That's what the side length exiting field is. Right. So we're trying to calculate the flux, how it changed in time. And all we said is, I'm changing the area of time. Area is decreasing as I pull this out. So let's start stitching all my things together. I have the side length. I need the area to calculate flux. So the area as a function of time is going to be A times B at t, or A times A minus VT. Just straight substitution.
Professor,
Yeah.
what is that word on the diagram next to velocity in front of the equal sign?
Oh, slope.
Slope. Okay, thank you.
Yeah. All right. All right. I need to erase it because I need the board space, but like keep this picture in your head, guys. Or yeah, keep this picture in your head, refer to your notes. I need to erase it because I don't have infinite board space. All right. All right. Now calculate that EMF, that induced EMF. E is change in flux over change in time. All right. So what we're saying is calculate the flux at t equals 0.1 seconds minus the flux at 0 seconds all over 0.1 seconds. The flux, right? This is going to be the magnetic field strength times area, or A times A times A, come on, minus velocity times 0.1 seconds minus, I need to dip into this space. Right. This is the first term minus V A minus V times 0 seconds. Right. Color code it if it helps. This term here is that guy. This guy is that guy. Just trying to color code the equations. Right. Let's start doing some simplifications. BA times A, that is BA squared. BA times minus V times time minus BA V 0.1 seconds. BA times A. Right. BA times 0 seconds. 0 doesn't matter. I don't see anything in the chat. So, all right. So from here to here, I just multiplied things out through the parentheses. And now look, I've got a BA squared minus a BA squared. So I just cancel those out. The EMF is equal to minus the term that survives minus VAV times 0.1 seconds, all divided by that delta T from the denominator. All right, well, fancy that. 0.1 seconds divided by 0.1 seconds. The EMF is just minus VAV. And since we're taking the absolute value, all right. Right. So I won't leave you guys hanging on just that expression. Let's plug in the values, right? The EMF. B, I said was 5 Tesla, let's see here, 0.5 Tesla. A, I said it was 5 centimeters. V, we're pulling this thing up at 3 centimeters a second. Right. So, the way I did this, I said this is 5 times 10 to the minus 1, 5, 10 to the minus 2, 3 times 10 to the minus 2. Units are going to be volts in the end. 5 times 5 is 25. 25 times 3, 75. All right, factors of 10. Minus 1, minus 2, that gets you minus 3, minus 2. Right. Times 10 to the minus 5 volts. Shift the units around if I want to. The EMF is 750 microvolts.
Microvolts is the unit that it should always come out to be.
Completely depends on the problem. It's always going to change.
Okay.
We're going to see how we can manipulate these. Let's see here. I thought RV was 5 Tesla. Let me check. What did I write initially? I initially wrote, let's see, page 3. Okay, Ben, you're correct. I initially said 5 Tesla and then calculated with 0.5. So easy fix. It's only a shift of 10. So this is 5. This will be minus 4. 75 microtesla. I accidentally wrote 0.5 Tesla instead of, or not Tesla, volts. I shifted my power to 10 by 1. Sorry about that. All right. So I got some comments I want to make. Am I safe to erase the big algebra? I'm going to wait like 5 seconds. All right. All right. I'm getting the cue. I'm okay to clear the algebra. All right. So comments I want to make. E equals Faraday's law. That's going to always be true. Faraday's law is always correct. E equals BAV. Right? Spoilers, you're going to see this come up a lot of different times. This guy will come up frequently. It'll be the square loop moving around. We'll have something similar of a bar sliding around a magnetic field. You're going to see an expression that looks either exactly like this or eerily similar a bunch of times. But do not take the shortcut and assume this is always correct. Do not make that assumption. If you do, you're going to screw it up. right? You will see expressions like this or similar to this all the time, but this is not always true. This type of expression completely depends on the problem we're doing. You need to always start with Faraday's law and show something like this comes out. Let's see. So, how we do? We got about 15 minutes. All right. So, one thing we're going to address now is this absolute magnitude. Why do we say Faraday's law is the magnitude of this change in flux? And we're going to tie this into current flow, right? All Faraday's law has told us so far is how much voltage gets produced. But remember that simulation, the light bulb, depending on how I moved the magnet, you might have noticed that the direction of current could change. So we ask ourselves, which way does the current flow? Let's do this by example, right? I'm gonna have a solenoid, comes out like this. A little switch connected to a battery. Boom. So here's my solenoid, and I'm gonna have just a loop by itself over here. Right? Right? So, when I close the switch, an EMF is induced in the loop. Must be, right? I close the switch, a current flows. Goes this way, comes out, in. Oops, make that up. So it goes out, in, out, in, out, in. So what kind of magnetic field? What kind of magnetic field does this solenoid produce, right? Remember our right-hand rules, right? I've got current at the bottom going into the board. So current's going into the board. I'm going to look at the magnetic field inside the solenoid. So current going in at the bottom. I want to know the magnetic field inside. So this solenoid will produce a magnetic field that way. Right? It's going to do something. Right. So this only happens the moment after I've closed the switch, right? Switch is open, there's no current, no magnetic field from the solenoid, nothing's happening in the loop. Close the switch, current flows, that creates a magnetic field. That magnetic field is going to induce a voltage on this loop. If there's a voltage on this loop, it's going to make its own magnetic field. So this is the game that's going to plague you for the rest of the semester now. Current flows, creates a magnetic field that induces a loop voltage over here. That voltage has a current. This current makes its own field. These are the games we're going to be playing now. So there's a voltage on that loop. What's the direction? right? Let's draw from the loop's perspective, right? Here's just the loop, and that loop's going to see magnetic field. I'm drawing from this perspective again, so it sees magnetic field. Right? So, does current go clockwise or counterclockwise? We know a voltage has been produced on this loop. If there's a voltage, charge must flow on this thing because it's a conductor. Charge is going to flow. So does it go this way around or this way around? I'm not going to jump ahead and just give you the definition. We're going to use an example to figure out why it should go one way or the other. I don't just agree with just laws or states of laws, right? We want some physics behind them, right? So, put this problem, right? Put it on the side for now. We're going to solve a related problem and then come back to the conclusion. Should it flow one way or the other, right? So, bookmark that for now. Let's try another problem. Right. I'm going to have what's called a slide bar. Right. So I've got these rails that go however long I want this thing, and this bar, it slides along, right? Think of it as like a knob in my electronics. If I slide the knob, I'm changing the electrical properties, right? And there's going to be some external magnetic field, right? All right, so here's the setup. I'm going to come in. This thing apparently currently has no additional flux, right? This would be the area that's being fluxed through, right? If I flick, I just flick the little sidebar, give it a little nudge, and the bar is going to start to slide. Look, the area will start increasing. Flux is changing, there's induced EMF. Induced EMF, there's a current. So let's assume that the induced current flows clockwise, right? Assume the current starts to go this way around. What is the direction of the force on the slide bar? All right. So I see a current through the slide bar going down. Remember, F on a wire is ILB. Then we use our right-hand rule to get the direction of that force. Right? So the slide bar, it has a current going down. There is a magnetic field going crosses, that's into the board, which means there's the force going that way. Does anyone see a problem with this picture? What I do to get this thing started going? Give it a little tap. Just flick. Just flicked it off that way. All right. So it starts moving. Let's say 1 centimeter a second. Going nice and slow. All right. I guess the direction of the current. The current's going this way. And then all of a sudden, it feels a force that direction. All right. What do I do if I feel a force that way? I accelerate. So all of a sudden, my little tap here has got this bar feeling a force, accelerating, pushing it this way. So if this is allowed to continue, this thing's just going to keep accelerating faster and faster. This bar is going to gain kinetic energy. It's going to move faster, faster. It's literally going to go Buzz Lightyear on us and fly off to infinity, because that's what the physics say, if this is correct. So, exactly, it'll slide by itself. That's physically impossible. I don't have infinite energy to slide this thing forever. So, conclusion. Right? The current in this picture has no choice, must flow counterclockwise. It must. If it doesn't, I violate physics. I guess I just got a perpetual motion machine, free energy. Doesn't work. So the current must flow counterclockwise. Right? What's the direction of the induced magnetic field? So the current must flow this way. If there's a current, this guy's creating its own magnetic field, so the induced field. Right? Direction of current, go inside the loop. Magnetic field coming out of the board. The induced field. The induced magnetic field points in the opposite direction of the external source, that external magnetic field. All right. So I think this is a good breaking point. Next time we'll come back to the loop. What's the direction of the loop in the current, or the current in the loop? And we'll introduce what we call Lenz's law and formalize what we just set up by example. All right, we'll call it a day here. Everyone take care.